Let's welcome our next speaker, Yiqun Xie from the University of Maryland.
So I will talk about improving theory-based simulation models with knowledge-guided learning. So from all the talks, we have learned that theory-based models enjoy a lot of benefits, including being interpretable and then less reliant on large volumes of training data. However, there are also limitations, including having very high computational cost from the complex modeling, and also many of the models rely on specific assumptions. And in practice, users may not know which model to use given a new application scenario. So I will present some new results that try to enhance these models. First, from the computational side, try to accelerate the models with deep learning. So this one, I will talk about the case study for base flow prediction in hydrological systems. So first, let me start with the computational side. And there have been a lot of efforts trying to scale up theory-based models using deep learning. For example, NVIDIA's recent foundation model called ForecastNet tries to accelerate weather forecasting, climate projection, and according to the results, and they can achieve speed up for hundreds of times while maintaining very similar results. And similarly, Google also has the GraphCast trying to do weather forecasting as well, and similarly for many other different domains. And most of these deep learning emulators, they have specific designs based on the characteristic of the physical model. And so in this work, we are trying to develop the first deep learning based emulator for the carbon forecasting problem in forest ecosystems. And so this is an important area because forest ecosystems play a critical role for carbon neutralization, global carbon budgeting, and looking at the numbers, the terrestrial ecosystems, including forest, they absorb about 1/3 for the carbon dioxide emissions from human activities. And the model we're looking at here is called the ecosystem demography model, the AD model. So this one is responsible for the forest component in the NASA carbon monitoring system, and is also a key component for the new global carbon budget. It's also been deployed for operational uses in the state of Maryland. And so we are working with domain experts, George and Lei. So they are the original creators for this ecosystem demography model. And George is also currently the science lead for NASA carbon monitoring system. And so in order to get the very high forecasting quality, AD relies on a large variety of different processes. And so it does the forecasting in a step-by-step manner along the time series. In every step, it considers over 100 variables as the input, and then try to estimate the carbon-related variables on vegetation height, above ground biomass, soil carbon, so on and so forth. So this leads to a very high computational cost. And so I will talk about several challenges for designing the deep learning emulator. So the first one is error accumulation. So this AD model is being used for long-term forecasting. So you're running the model for 40 years, 100 years, 200 years. And during this process, the small errors at local steps can very quickly accumulate to very large errors towards the end of the forecasting. And so we have a couple of designs trying to reduce the error accumulation. So the first one is very intuitive. So basically, along each of the forecasting sequence over the long term, we are trying to encourage error cancellation during the process instead of letting the error becoming compounding errors and then have a very large accumulation. And also we have algorithms that try to make the loss calculation more efficient for this error cancellation. And also when you train the model, if you directly train the model at very fine temporal granularity, and then you will see a large volume of local variations, and also that increases the number of steps, and so more error accumulation. And so in order to address this, we decompose the training into multiple temporal scales. So if you have the combination of the temporal scales, you can still get the forecasting at any time step you want, but you can reduce the error accumulation effects. And the second challenge is looking at the output carbon variables. There are heterogeneous patterns. So someone like the above ground biomass, the second one, it tends to have a more stable growing trend over the years. But if you look at the bottom left, gross primary product, GPP, it doesn't have that pattern. It tends to have very large variance over time. So we are trying to summarize those time series patterns from the training data and then try to insert that as prior knowledge to guide the forecasting of to guide the forecasting process. However, not all of the patterns are actually useful. So some of them, if you have very large variance over time, they actually tend to hurt the forecasting process. So we also have a statistical component in there trying to automatically determine whether the variable forecasting should include the pattern or should skip the pattern. So we did some testing in northeastern US. So the data covers about 40 years under different forest initial conditions. So this slide just shows some numbers that the proposed deep art model outperforms the baselines, but this may be better, this visualization may be better. So on the left side, you're seeing the original ad forecasting results over 40 years. On the right side is the deep learning emulator. So you can see the forecasting can pretty well resemble the original one on the left. Now, in terms of the computational time, this is not really an apple-to-apple comparison because the ad model has to run on CPUs, but the deep ad is running on GPU. However, looking at the time difference, it still seems to be very promising. So for the ad model, the same task will take 192 CPU hours, but for the deep ad, it's only 0.02 GPU hours. And so now we are also working to create a global scale data set over maybe 40, 100 years under different climate scenarios with benchmarking machine learning models. So we hope to post the data set online soon so that others can also play with the data and try to further enhance the forecasting of carbon. So this is for the computational side. And then second, I will talk about another work that tries to integrate multiple physical models together to enhance the prediction quality. So for example, in base flow estimation, there have been multiple models developed in the past decades tries to estimate the base flow. And so our domain collaborator, Dr. Liang from University of Pittsburgh, they often find it challenging to determine which model should they use for a new study area. So now in the knowledge-guided machine learning context, this means which model or which models should we use to integrate together to guide the training and adaptation process of these machine learning models. So we developed this physics-guided meta-learning approach. So this is built off the model agnostic meta-learning paradigm. So as you know, it is normally impossible to find one set of parameters that can be optimal for all different tasks. So in the MAML paradigm, basically we try to find the initial condition from where we can quickly adapt to different tasks using very small amount of training examples. So the original MAML algorithm is purely data-driven. It doesn't really consider any physical guidance. So in this work, we try to have different designs to inject the knowledge guidance into the meta update process. So we can make the updates fine-tuning more effective. So for the case study, we looked at 60 river basins in Pennsylvania. And then here are some example results for one river basin. So the x-axis is the time series. And then the black dots in here represent the true reference. And the blue curve is the deep learning pure data-driven results. So you can see in general, it works well on the left, but it misses the abrupt change in the middle. But if you add the knowledge guidance, it can recover this peak. And the right side may be more interesting, where we only use very small amount of training data to understand the behavior in data sparse scenario. So in this case, you can see the blue curve no longer works very well. The pure data-driven model will have large deviations from the true reference, but the knowledge-guided model can maintain a pretty stable prediction quality. So those are the results that tries to integrate learning with the theory-based models. But in many cases, you don't really have the very nice theories being developed. So I will quickly go over two other examples where you can also incorporate general knowledge, for example, general knowledge about spatial and temporal patterns into the machine learning process to enhance the quality. So the first one is the knowledge-guided self-supervised learning. So from today's and yesterday's talk, we have seen the importance of having close task alignment between the pre-training task and also the downstream task. So in the large language model example, so you can see during the pre-training process, we can mask out part of the synthesis and then try to predict it using the previous one. So this is very similar to the actual downstream task where you send a sentence to the ChatGPT and then based on that, it try to write you a response. So there is a very close alignment. But if you look at many science questions, and for example, in remote sensing Earth monitoring, so there is actually a very loose alignment. So for example, during the pre-training, we are using mask autoencoder, try to fill the gaps in the images. But the skill that you learn to fill the gaps is not really correlated with the downstream task. For example, every pixel, we try to classify it into different land covers. So there's very loose correlation. So we're trying to design self-supervised learning methods, which can align very well with the actual downstream task. And I will use the satellite image cloud masking as one example. So cloud masking in satellite is a very essential pre-processing step, which is mostly needed for all the Earth monitoring tasks, because you have to first remove the cloud and then do your analysis. And so here, we're trying to use the spatial temporal knowledge we're trying to use is the difference in the cloud dynamics and the Earth surface. So if you look at the pictures, at the same location, if you look at the cloud pattern in the top row, they tend to be random and they can change quickly over time. But if you look at the land surface, they tend to have more gradual changes over time, and then over different years, they may have periodicity. However, the key here is if you want to observe this gradual change on the land surface, then you have to mask out the cloud in the first place. So there is a certain dependency in here. And this is what we are trying to leverage during the design of the self-supervised learning task. So if you look at this example, by looking at the overlap between different satellite images, you can determine which ones are more similar, which ones are less similar. And so now you have your real task to do the cloud masking. And then in the self-supervised learning task, we are trying to have the model estimate the similarity relationship between these different pairs. Because we're generating the data, we know which one is more similar, which one is less similar. And in order for the model to estimate the relationship, it has to mask out the cloud in the first place. Otherwise, it's going to pollute the result. So this dependency allows us to do this training in a pretty much label-free manner. And so there's a very close alignment between the real task and the downstream task. So we did the testing in multiple different satellite platforms. They have very different spectral bands, different resolution, and the model seems to be work pretty robustly across the platforms. So here, the second column shows the cloud masking result, which aligns pretty well with the visual reference on the left for the thick cloud and thin cloud. And so the final example is for variability aware learning in space. So here we are trying to leverage the spatial knowledge about variability. And so here I will borrow one nice example from Dr. Shashi Shekhar. So looking at the three pictures, and you can see they all have very similar visual characteristics. And so if you look at the pixel value, and they can also be quite similar. But if you add the locations, and you will see they are actually representing very different geospatial phenomena. The first one is salt, and second one is sand, and only the last one is snow. So from this simple example, you can see the functional relationship from the input X to the output Y will be different across different geographic regions. So if you try to force one model to make all the predictions, let it be a foundation model, and you may get actually pretty poor result. So to address this, we have this variability aware deep learning framework, which is going to automatically optimize the partitioning of the space to separate those regions with potentially different functional relationships. And it does this in a hierarchical manner. So you can get arbitrary number of partitions you want. And also there is a significance testing component to help you automatically determine when to stop the hierarchical partitioning. So this shows a large improvement for land cover classification in California in our testing. And so the paper got the best paper award from SCDM 2021. And I think this is pretty much all I want to share. Thank you very much. Please let me know if you have any questions.
Any questions from the audience?
Thank you so much for your presentation, and I'm really interested in your deep ED model, and I'm really surprised about the error accumulation can be reduced by your algorithm, and I want to know whether that kind of reduction is from your deep ED or some coherent other statistical algorithm. So. And also, beside that, I want to know whether the ED model itself will have such accumulation error.
Yes, that's a very good question. So there are two questions. The first one is on the error accumulation. So the results actually show the model can reduce the error accumulation, but you will still see error accumulation over time, but just the scale is being reduced. So we are still trying to further enhance the algorithm. So if you want to completely get rid of it, it's quite difficult. And we also try to so when you train the model, normally you use the perfect data. So the initial condition is being given by the ad model, but when you do the long-term forecasting, then you will have to do it in the autoregressive manner. So your input may no longer be very perfect. So you can also try to inject errors in the data set in order to further reduce that accumulation. But this is a very challenging problem. So you can reduce it, but very hard to get rid of it. And then the other question is about the ad model itself, whether there's error accumulation. So this one, so there are two parts of the question. So currently, we are only looking at the simulation model itself for the forecasting. And so it's considered as the gold standard. But if you look at the real data sets, if you compare to sensor observations, and then sometimes the ad model certainly will have errors as well. So that's a component we haven't considered so far in this computational experiment. But later on, we plan to also incorporate more observation data, for example, from the multiple neuron sets in order to look at the error accumulation from ad itself and try to further enhance the prediction quality.
Any other questions?
I think I'll just have more of a comment. I think this is working. So I think your observations about making sure that the self-supervision task is connected to the downstream task is extremely important, because oftentimes people would just blindly use whatever comes to their mind.
Right.
So I think there's a lot of room for future work in that direction. That is making sure that people are aware of how do you choose the right task.
Yes. Thank you for the comment. Yeah, that's indeed very important. We actually did some testing that if you use that self-supervised learning task that is not related to the downstream task, actually the improvement you can get all of it is very limited for the actual downstream task.
Yeah, thank you for the talk. And I'm very interested in the data set you mentioned for the CO2 forecasting.
Yes.
So is it a simulation data or is it actually observation data?
It's a simulation model, but it's tailored based on real observation data.
I see.
Yes.
So yeah, we have similar challenges before, but I guess asking your feedback on this is people always questioning about, okay, how your simulation data will actually be good for training the model, right?
Yes.
I mean, or how good quality your the data that you plan to share. Any way to evaluate that? Or
yes, that's a very important question. So our domain collaborator also faced similar questions. So they actually did a global scale evaluation of the data set at different locations. And sometimes they have the carbon towers to get very detailed measurements from local places to compare with the model. And sometimes they have the satellite observations at the very large scale to make the comparison as well. So they did do very extensive evaluation. So in order to get the model used in the operational cases. Yes. So the data we will share will also be calibrated based on the real observations as well. Yes.
Okay, thank you. Thank you, Yiqun. So let's move on to the next speaker, Gengchen Mai from the University of Texas at Austin.